Okay, today, and you can ignore all this stuff on the board, we'll develop this as we go, but I'm going to use the blank part of the board to write some stuff down, kind of in the order in which we saw it in class, give myself as much room as possible. First task, I drew an incline, and this horizontal, and I drew a block, and I said, sketch a picture, sketch this picture, you know, any angle you want with the block, as long as it isn't flat or vertical, and then show me an applied force, a vector, representing an applied force that's acting below the horizontal. Okay? So, you know, very typically, actually, I didn't get much. From a bunch of people who've had some prerequisite courses where you've done this, not prerequisite courses, but other courses, is a little surprising. But a typical picture maybe like this. Okay, so here's your force. Then, you know, after a little nagging, I got people to actually label that force. Okay? So we got a picture that looks like this. Then I said, okay, that's great. Now let's have that force with its initial point at the center of the block and make it at least 3/4 as long as the ramp. Okay? So, you know, people then go, okay, here we go. Here's now my F applied. I said, okay, that's great. Okay, then I said, let's see, what did I say? I said, okay, should have looked before I went on because there's several orders in which this could have been done. Then I said, okay, sketch vectors corresponding to all the other forces that would be acting on this. Inevitable, you know, the inevitable forces that would be acting. Well, yeah, people did pretty well. But, you know, there's some anomalies. Okay, you have a gravitational force acting downward. You have a frictional force. Now, the frictional force could be either acting upward or downward. If the object is stationary, then the frictional force is probably acting upward. So here's your frictional force. Okay, and then what else? Well, there's a normal force. Okay, so we have a normal force. Now, if this object is stationary, all these forces are in equilibrium, aren't they? And if it's accelerating, well, then some of these, you know, the result of all these forces won't be zero. The sum of all these forces won't be zero. Having sketched this, I said, okay, now sketch a vector for the displacement along this, for a displacement along this ramp. Now, some people sketched a vector this way, some people sketched a vector this way, and either is possible. Okay, under the influence of these forces, it's entirely possible that F applied is sufficient to overcome the friction in a way that we'll see, and the object will move up the incline. It's also possible friction is much higher, and the object would not accelerate in this direction, but could still be moving in this direction because we could have given it a good push to start, and it's not come to rest yet. Or it could be moving down the incline. Okay, so or it could be stationary, but the instructions just sketch a displacement, a possible displacement. So any vector parallel to the incline would be okay. So I sketched a displacement in the downward direction, but not everybody did. Okay, then I said, okay, now sketch the projection of every vector onto the displacement. So, well, gravitational vector projects onto the displacement. So we have this. I'm not going to label it. The picture's already small enough. but that's the parallel component of your gravitational force. The component of your gravitational force parallel to your displacement. Now this is going to get a little messy because of the way I labeled this, and I'm going to have to kind of go through my labeling of the frictional force in order to project the applied force that I happen to have here. So we have a right angle here. We go from the tip of the vector at a right angle till we hit this line. So here is the vector projection of the applied force. Now, the other forces are either parallel or perpendicular to delta S, because the normal force has to be perpendicular to the incline, and if delta S is a displacement along the incline, then this thing is perpendicular. So its projection on the displacement vector is 0. And the frictional force is its own projection, because it is along the direction. Whether you drew it this way or this way, it will be its own projection on delta S. So these are the vectors, and I'll observe, and I didn't say this in class, but I'll observe right now that had you sketched delta S in this direction, these projection vectors would be exactly the same. Your delta S might be this way, but the projection vectors, the gravitational force, would still project over here, and these two vectors would still project to the right. So it doesn't matter the direction of your delta S. Now if you're calculating this, if you're using the angles and stuff, you do have to be clear about what direction you want to use for delta S. Okay, but that all works. Okay? Well, the next thing I asked was, okay, let's get the vectors. So let's get the component of each vector perpendicular to delta S. Okay? Right here's your F grav. The component perpendicular to delta S would be the vector from here to here. This is perpendicular to delta S, and if we add it to the component parallel to delta S, we get F grav. Now with F applied, well, the component perpendicular to delta S is here. So, it's going to get a little messy, so I might not label any of these. Also, the component of F norm, the normal vector, perpendicular to the delta S is just this. So now we have a picture, and it's a redundant picture in a sense that I'll talk about in a minute. We have a picture of F applied, but also of its components parallel and perpendicular to delta S. Now, and same with F grav, but let's focus on F applied first. So this component and this component add up to this vector. So this component and this component are completely equivalent to this vector. And we've only got F applied acting once, but with the picture here, if we include all the vectors that are now in the picture, we've actually got F applied twice. Once because we've got it here, and once because we have its two components. So what I'm going to do is I'm going to put a little wavy line through the F applied vector to say, okay, I'm taking that out of the picture. That's not really one of our forces anymore. Okay, then we have the F grav, and it's the same thing. We've got the two components. We don't want to have F grav in there twice, but effectively we do. We have it here, and we have it for these two vectors. So I'm going to kind of leave it there, but I'm going to put the little wavy line through it to indicate that we've replaced it with something else, in this case with these two vectors. So F applied has a wavy line because now we've replaced it with its two components, and F grav is now gone because we've replaced it with its two components. F norm is still the same vector it was, I just colored it because now every vector that's left on here is colored. Okay? The orange vectors are perpendicular to delta S. and the yellow vectors are parallel to delta S. And if we put all these vectors together, we have exactly the same forces that we had when we just had F applied and F grav without any of the components. So now we have a nice set of vectors in this direction and a nice set of vectors in this direction, and we can proceed with our analysis. Now we have to be able to calculate these vectors, but once you've got the picture, that's actually usually pretty easy if you have enough information. So there we have the overview of the scheme that we talk about in class, and now we'll go through some of these diagrams.